Hello, everyone. My name is Jay Mahajan, and this is a quick review of inverse kinematics. So let's talk about inverse kinematics. What is it? So recall that when we did forward kinematics, we took our joint angles and we tried to find our end effector position. With inverse kinematics, we have to find our joint angles, but we're only given our end effector position. So we're really going from our end effector to our joint angles. Now, there are two major ways of finding inverse kinematics for any robot. The first is using an analytical approach. So given a few measurements like link lengths and some defined vectors, the joint angles could be found using basic trigonometry. The second is using a numerical approach. Our robot is just too complex, and doing all the trigonometry might be taxing. So this essentially becomes an optimization problem, which we'll go into later. So let's begin with our analytical approach. Let's first define a vector v of I from the base of our joint to the end of our joint. So I've highlighted them in red here for each joint, 1, 2, 3. And then we realize we have two frames of reference we're working with. We have a space frame here, and we have a body frame. And assuming this angle from space to body does not change, we can derive this relationship. And you can see from the vectors that this adds up. Now let's define a couple more variables. I know this is going to get a little bit messy, but let's just focus on this one for example. So we'll define L of I comma 1 to be the length of the first leg, and L comma I2 to be the length of the second leg. So for example here, this is the length of the first leg, this is the length of the second leg. Let's define alpha of I to be the angle between these two legs. So we have this angle right here and this angle right here. And that is our alpha right here, alpha 3. And remember, now you can clearly see with V, with your L's here, you can find alpha, alpha I. And this works for all three joints here, since they're all vectorially related. And you get this cosine relationship. After that, we realize that our alpha plus theta should equal 180. So then our theta at I equals 180 minus alpha at I. And this robot isn't particularly complex because they're all, the vectors are kind of attached to each other. They're not as bad. But what if we had a robot that was just way too complex, right? So this begins our numerical approach then. So our robot just has too many joints, or just physically hard to measure all the lengths. So it's very difficult. So ideally, we need to use numerical inverse kinematics here. So ideally, we want to find some t of theta that equals x, some transformation matrix that lets us equal the end effector position. And remember, if we solve for this, t of theta minus x, and we'll let that equal g of theta, this all has to equal 0. So this becomes a question of, can we find the roots of g of theta? And one such approach is using the Newton-Raphson method. So we can assume first that g of theta is a differentiable function, and we'll give an initial guess for theta. And some good initial guesses might be 0, the current joint position, and the highest possible joint values for each joint. After that, let's Taylor expand g of theta at our guess and solve up to the first order. Once we do that, we'll set that entire approximation equal to 0 and solve for theta. So in this case, we have g of theta plus the derivative, the partial derivative with respect to theta, evaluated at our initial guess theta 0, times our change in theta equals 0. Now, if we work out this equation and make it solve for theta, we get theta equals our initial guess minus our partial at theta, evaluated at our initial guess, inverted, times our g function inverted of theta. Now, if you realize that our partial here, this partial equation, is equal to our Jacobian, so then we can substitute our Jacobian and solve, this is the equation we can get. So we get theta equals our initial guess minus our inverse Jacobian times evaluated at our initial guess times our inverse g function. Now we repeat this for k iterations with our new estimate equal to our initial guess. So you can see our new iteration depends on our previous iteration's guess, evaluated at our Jacobian and our function here. And our stopping condition is when our previous iteration and our current iteration are below some value of theta here. And the norm of these two is below some theta, some epsilon here, sorry. Once we reach that, we've successfully found our thetas that could be our joint angles. And there's multiple answers here since g of theta is multi-valued here. So here's an example we have. So we have this little robot here. Our first thing we should do is find a T matrix. So our transformation matrix, which is our rotation, a point at 0, 1. And then from there, let's find our spatial twist for each of these joints. So we have 1, 2, 3, 4, 5, 6. So we'll find 6 spatial twists. And then we can give an initial guess for our thetas. So for now, I'll just use 0. And then we just plug into our any type of coding environment. So you can use Python or MATLAB, and you can just use the modern robotics library. And so if you're working in space frame, you want to use the icon space frame, or you want to use, if you're in body, you want to use icon body. And this is some snippet of code that you use. And this is where our epsilon values that we set are really low here. And if the function completes, then we're going to print out our values.